Take a look at the flawless diamond on an engagement ring, the lead snapping in your standard pencil, and a freak, violent kitchen explosion. Though they look completely unrelated, every single one of these items and events is an expression of the exact same elemental building block. The physical world around us isn't constructed from a static inventory of materials. We live in a reality built entirely on shape-shifting matter. Meet carbon, atomic number 6. It possesses a unique chemical superpower called allotropy. This means identical carbon atoms can exhibit completely different physical properties based entirely on how they are arranged. When pure carbon is subjected to extreme heat and crushing pressure deep underground, it becomes diamond. In this tight configuration, it forms the hardest natural substance known to science and refuses to conduct even a single drop of electricity. While we prize that hardness for jewelry, its highest utility is found in factories and mines. We rely on those crushed, heat-forged carbon bonds to tip heavy-duty rock drills and industrial marble saws. But if you simply flip the molecular structure, you get graphite. The material suddenly becomes entirely opaque, incredibly soft, slick to the touch, and highly capable of conducting electrical currents. There is even a third, stranger configuration. If you link up exactly 60 carbon atoms, you create Buckminsterfullerene, a bizarre, hyper-stable microscopic structure shaped precisely like a soccer ball. The physical limits of a substance are dictated entirely by how its atoms are physically locked together, not by the raw chemical ingredients themselves. When you introduce hydrogen into the mix, carbon bonds with it to form hydrocarbons. In their raw state, these are typically colorless, odorless gases, but they act as the primary structural building blocks of global energy. The simplest of these are saturated hydrocarbons. They are held together by basic single-bond geometry, forming straight, stable chains. Increase the complexity, and you get unsaturated hydrocarbons. This happens when carbon atoms start sharing double bonds, creating alkenes, or even triple bonds, known as alkynes. These carbon chains can stretch out into long, straight lines, known as aliphatic structures, or they can twist and loop back on themselves to lock into perfectly circular, highly stable aromatic rings. These tiny, microscopic variations in geometry, switching between rings and straight chains, provide the exact hidden scaffolding required for nearly all modern human manufacturing. In 1846 Germany, a chemist named Christian Schonbein was experimenting in his kitchen using highly volatile mixtures of nitric and sulfuric acid. He accidentally knocked over a jar of the mixture. Grabbing a cotton apron to wipe up the spill, he inadvertently triggered a rapid chemical reaction that led directly to the creation of the first modern synthetic polymers. We know these polymers today as plastics. They are constructed from massive, incredibly long carbon chains with high molecular weights, engineered to be extraordinarily resistant to corrosion. One category is thermoplastics. Because their internal polymer structures remain linear, you can heat them, melt them down, and continuously bend them into new shapes. But thermosetting plastics operate under entirely different rules. Their polymers are heavily cross-linked. Once a thermoset material like Bakelite is molded and cooled, its internal structure locks permanently, making it immune to melting ever again. A simple kitchen error taught us how to hack the carbon element, giving humanity the ability to forge permanent, artificial materials that never existed in nature. This mastery over structure extends to elastomers, specifically rubber, built around a base organic polymer called isoprene. These elastomers feature massive, coiled, chain-like molecules. You can stretch them out to extreme lengths under heavy tension, and they will snap completely back into their original shape without taking damage. To feed the immense global demand for this material, millions of tons are produced annually, starting as thick, raw white sap manually extracted from rubber trees deep in Asian forests. From crushing pressures forming crystals deep in the Earth's crust to engineered synthetic casings and flexible elastic chains, the modern world is an empire built out of carbon. Every time you stretch a band, flick a light switch, or scratch a pencil across a piece of paper, you are interacting directly with the most versatile elemental alchemy in the universe.